We're in week 3, class 3, and we're going to look about rotational stability of rigid bodies in space. So satellites, anything in that movie Gravity would fit in here beautifully. And the basic premise is that the energy, if the rotational energy is equal to or dissipating, that the measures of the stability of that, if it spins, and we know it's already going to be stable if it spins about a major axis. Now I'm going to show you a little bit why the equations say that's true. So the major axis of this aircraft, of course, is the z-axis. So we would expect that if this aircraft ever got into a flat spin like this, so that would be the worst condition to try to get out of, because that's where the airplane energy, that's where nature wants it to be. And that's exactly right. A flat spin is usually a time for the pilot to bail out and get out of it. So that's one of the maneuvers you never want to see, and it's because of the way that these equations work out. So we're going to look at the rotational energy. It's given by a simple vector inner product that you end up with. The energy turns out to be, notice I'm using the diagonal form, so I'm going to use City's notation of the I just to remind you that I'm using the diagonal form. If I use the J's, you might confuse it with an airplane looking like device. But this is a symmetrical satellite, and later on we're going to assume that IX and IY are the same. Our angular momentum is given by the vector IX omega x. Since it's diagonal, it's going to be pretty simple. And then we're going to be looking at the magnitude of that vector, or the magnitude squared, which is just each of these elements squared square root. So these are the two basic equations we're going to look at investigating the Euler equations right here. And these are just reproduced from what we did yesterday. So let's start out with a spinning disk. And the cool thing that we can be able to do with the omegas is we'll be able to visualize the omega as projections along the I, J, and the K axes. So your omega vector, and for today, our omega vector, we saw the vector in space. And of course, either PI or BI, it doesn't matter, but I'm using the P for principal axes. So the tip of that vector is going to nutate in space. But what is not going to nutate in space is the angular momentum vector. The angular momentum vector is going to be fixed. So if I were to draw this vector, and let's just say I'm going to draw it like this, H, and the omega vector gets to nutate and rotate around. And of course, as it nutates around and rotates around the body axis, of the disk itself will nutate, and that's what we're going to look at today, that kind of thing. But what I want you to remember to start out is that the angular momentum is fixed in space. That's a nature thing. And then the angular velocity vector, with the components omega x, omega y, omega z, it can nutate around. So to start the investigation, what we look at is the case where omega z, the z component, is constant, like a spinning disk. So we have a large spinning disk, and the z component, whenever you see the omega 0, that's the z component, and it's constant. So the omega x and the omega y are going to allow it to rotate in this plane, in the body axis, and the z component, if put in body axis, will be a constant. So we're going to kind of investigate the motion. I took this first Euler equation, differentiated it, then I substituted the corrected second equation for Wy dot, and when I did that, I got this harmonic equation in Wx double dot, which has a frequency that's a function of omega z, the spinning, and the relationships between the moments of inertia. You see that? So again, just if you took the Laplace of this, you'd end up with s squared plus lambda 0 squared is equal to 0. That's a harmonic oscillator with roots on the plus or minus j omega axis, as long as this is a real frequency. I can't have this coming out to be a negative number. If, for example, if this turned out to be a negative number, then I would have roots here and here. I have two real roots, one of which would be in the right half plane. So this is the condition. This would be unstable, right? If this turns out to be not a real number. So that's our condition for stability. Our condition for stability then turns out to be that our frequency turns out to be a real frequency and not a root that has a positive and a negative value, one of which is unstable. Okay. So what are the conditions for this to exist? Well, if IZ is dominant, then this will be plus, that's plus, 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 we're good. So if IZ is dominant, big fat disk, right? Sewer cover, it's going to be stable. If IZ is not dominant, and this is bigger, and IZ is not dominant, and YY is bigger, I have minus, minus. I'm good. I'm good. So, for example, if IX equals IY, say I'd have a pencil. This would be a pencil. This would be minus, this would be minus, but the product would be plus. So a pencil would be stable. I'm good. Okay? The only time that I'm really screwed is if one of these terms is positive and one of those terms is negative. So if you have a body, moment of inertia, where the IZ is in between X or Y, either way. In other words, if I'm spinning about an intermediate moment of inertia term, I am unstable. There's a great demonstration of this on my website. I got an astronaut dropping, I think it's an iPhone or something. He drops an iPhone and he shows, he spins it about its intermediate axis and he shows how it immediately flips to the maximum, going about the maximum. So this is the equation that we use to show you that your system is stable if it's spinning about a maximum or a minimum moment of inertia. Got it? And we talked about that yesterday. So if I have a sewer cover or a football that I've kicked and it's going end over end, it's going to be stable like that forever. If I have a bullet or a pass, you know, a pencil, if I'm spinning a pencil, it's also stable because of this equation. Yeah. Okay. Won't spin there. So a bullet will spin, a football will spin, and over it. So didn't yesterday we say that a vehicle wants to spin about its maximum? Well, what's that about? Well, there's no energy dissipation in this. Remember the Explorer satellite that we sent up into space? It was fine until they deployed the antenna. Once they deployed the antenna, you have energy dissipation. And when you have energy dissipation, this criterion does no longer hold. So you don't have a harmonic oscillator, you have a dissipating energy condition. The math is more complicated. Okay. It's in my notes and it's in the city book. He covers it using notation. And what I'm going to do in the last 15 minutes here, I'm going to describe the solution for that, but I'm not going to go through it. Now the other thing I want to show you here is that I could have differentiated the y equation first with y double dot, and then substituted x dot into it, and got almost exactly the same equation. So omega x and omega y turn out to be rotating in the horizontal, in the ij plane. They end up rotating in it, right? And because they're rotating in it, it turns out that the magnitude of them is a constant. In other words, what I'm saying is omega x squared plus omega y squared is a constant. Now, I knew this from previous dynamics work, but Citi does a beautiful proof of this. He just differentiates that. So he just differentiates that. So you're gonna get 2 omega x dot is 2 omega y dot equals 0, right? And Citi takes those two equations that I just manipulated into that. He adds them together, and he comes up with this equation, and he says, therefore, this is a constant. I thought the way he did that was just very elegant, very nice. So that means that your omega x vector added to the omega y vector, if we call that omega xy, so we'll have an omega xy in this body axis, omega xy. That's constant. So the omega xy is rotating at lambda 0 in the body disk. It's rotating, it's nutating around at a constant like so, right? And then you can start to visualize this motion. Again, I am the H vector, right? Well, no, let's not do that. Let's make this the H vector. This is the H vector. It's fixed in space. It's fixed in space. This vector rotating around the body axis, like so, nutating, right? And this is staying fixed. And of course, as this nutates about, it's carrying the disk with it. So if I start out like this, if I start out like so, this intersection point, the yellow cone is going to roll, with keeping the tangent, it's going to roll about the H vector. You see that? The yellow cone is going to roll, the tangent point is going to roll all the way around. It's going to roll around. So this is rolling about the H vector like so, and as it rolls about, the disk nutates. That's stable. Spin the top and watch it. It's in there, and you see what you can see. It's little kind of nutates, just like that. Hard to see the H vector because it's fixed in space, but that's basically how it works. What happens if I have a pencil? If I have a pencil, so I got a pencil now instead of the disk. So now I've got this. I've still got the H vector fixed in space. However, the pencil, when I do the math for the pencil, the cone goes outside, like so. The cone goes outside. Now the nutation angle is the angle between the H vector, which H is fixed in space, and the K body axis. That's your nutation angle. So I think they call it theta nutation. But this time, the tangent point is going to roll around the outside. It's going to roll around the outside. So the pencil that's hooked up to it is going to do this kind of a motion. And if you have energy dissipation, that motion is unstable. Okay? So the pencil that starts out rotating like this at a high spin rate, as it wobbles around the H vector, will start to tumble this way. And when it tumbles around that way, it'll become a disk. And when it becomes a disk, it'll go inside and then become stable for its rotation. So if you were to watch this in space, and there's a great astronaut, again, the video on the PolyLearn site, this thing is spinning, then it'll start to do this, then it'll go start to do this, and then the plane of this thing will wobble a little bit as it goes until it finally stops. That gives you a really good idea how that stuff works. Okay, so let's take a look. If T dot is negative here, then I want my theta nutation dot to be what? Positive or negative? Negative, right? Because if the nutation angle gets bigger, then I'm going to diverge away, and so I want my nutation angle to be negative. So if this is negative, then we want this guy over here, assuming these are positive to start with, IZ must be bigger than IX. Okay, IZ must be bigger than that. Therefore, if you have energy dissipation, you have to be oscillating about the major moment of inertia. The football pass eventually will tumble. Yeah.
Can you give an example? So was IX bigger than IZ, and that's why?
Which one?
Can you give an example compared to was IX larger than IZ, and that's why?
IZ is the spinning, is the moment of inertia about the z-axis.
Yeah.
So it's really IZ is that.
Yeah.
Right, and IX is big.
Yeah.
So when IZ is small, then this becomes negative. If that's negative, then this is positive.
Yeah.
So then the nutation angle then will diverge. So this gives you great tools to visualize